Doesn't it seem like these days that we don't just have one system? It's always a system in a system, or a system in a system and an even larger system. And then it's just, well, you get the picture. One engineer's system becomes the next engineer's component. This is system-level reality, and it's probably way messier than I can adequately draw here. Between suppliers and components and software, what we really need is optimization and more levels of abstraction to help get all of this somewhat figured out. Hi, I'm Amelia Dalton, host of Chalk Talk. Today, system verification is more important than ever before, and more complicated than ever before. Today, we're talking about intelligent system design with Frank Schirrmeister from Cadence Design Systems. Frank and I take a closer look at the optimization of electronics for system-level performance and how digital twins, shifting left, virtual system platforms, and emulation can help you unravel all of this mess and get your design to market a whole lot faster. All right, let's go. Oh, and before we get started, don't forget to click that link. There you can find even more information about Palladium and Protium platforms for system development from Cadence Design Systems. Hi, Frank. Thank you so much for joining me.
Hey, Amelia. Thanks for having me.
Okay, so today we're talking about digital twins and systems of systems. But first, Frank, how would you define a system of a system?
Well, system of systems is a term we have been using for a while now to essentially identify and point to complexities beyond the realm of what we've been dealing with. I'm a chip guy, system development chip guy, and the system around me is the bigger system. That's the board that becomes the product. And then with the system of systems, we're really referring to things like the F-35 strike fighter. So you have a airplane, you have a car, you have like lots of parts, lots of suppliers, you have lots of software in there. So it's really a system of systems where the system is so complex that it is essentially a system in itself from a complexity perspective.
Okay. So for all of the many pieces of this system puzzle, I would imagine, Frank, that optimization is key, right?
Yeah, optimization is really key. So if you look into a system on system and you decompose it here, like with the strike fighter, and by the way, these are all conceptual. I actually haven't disassembled a strike fighter myself.
Okay, I was going to ask you that.
It would be fun, but yeah, my backyard isn't big enough. So you have things like the broadband components, hatch mounts. At the end, you have chips going into all this. SoCs with software. So you have to optimize for this across the different levels of complexity, across angles like compute and communication performance. You have to do the electromagnetic thermal components, all of those combined. You have to optimize for safety, security, and quality. And what's interesting, you can't always do this at one level of abstraction, right? So
Sure.
Sometimes you need to be able to dive down deeper into, hey, I have this new system, this new subsystem in my system with new chips. I need to make an educated decision whether the new chip fits into the system environment just fine and what does it do to throughput, to the thermal, optical, mechanical performance of the overall system. So those are items which have to be considered across the different levels.
So I would imagine that the different levels of abstraction in the development of each parts of these systems would play here a big role.
Absolutely, they play a big role. If you remember Hitchhiker's Guide to the Galaxy, there's this guy, Slarty Bartfrost.
Yes.
So he designs Earth. And, well, if you design Earth, let's just take it small. Let's just take the Bay Area, right? So if you are Slarty Bartfrost and you're designing the Bay Area, you climb up onto Mount Hamilton and you're like, okay, where are my big points, right? So you don't start with putting Frank's house somewhere in Santa Clara. You basically said, oh, here are the major cities. I have the big city, San Francisco by the Bay. I have San Jose and Santa Clara, and let them fight about who's the capital of Silicon Valley with Palo Alto in the mix. And then I put the stadium for the 49ers somewhere and the Earthquake Stadium for the soccer guys. And I look into communication paths. So all of this I do at a higher level of abstraction, and then I refine down when I'm eventually at one point arriving at the very low level components, lots of houses to be put together on streets, all with cable and electrification and all that. And so again, the interesting design challenge now is you need a certain amount of accuracy to make educated decisions, but you also need a certain amount of capacity to make sense of the whole system, right?
Right.
So that's why the process of development is so interesting, and that's why we have now tools where you have abstract descriptions at the UML, SysML level, but then certain items require full fidelity for your electromechanical and the thermal solving. You use tools at a gold standard accuracy level lower down. Same with things on a chip, so different levels of abstraction comparison on a system on a chip. You want to look into the communication patterns between the different blocks, and you ideally would want to have the full accuracy to do it, but then to simulate all the different cases, all the different ways the different blocks can communicate and what the bus delays, the interconnect delays may do to that. It takes a lot of time. So there are now assessments, what can I do at a higher level of abstraction and for what do I need much more fidelity? And that's a design and verification challenge.
Sure. Okay, Frank, so what about this digital twins part of the story here? Now, I know about regular twins, but digital twins?
Well, digital twins, it's one of those words which has made into the buzzword bingo
Sure.
environments, if you will. It's sometimes overused, and I'll define how we use it here in a minute. But in general, if you look at a digital twin, it's really meant to be a digital representation with which you can do similar things as you can do with a real implementation of it. If you take a car, you really don't want your test drivers to be exposed all the time to all the extreme ends of what the car is specified for,
Sure.
or even above that. So for that, having a digital representation, a digital twin for which you can now push the environmental data further than what a normal test driver would be able to deal with, that is a very useful thing to have to do analysis and to extract data from. Same with longer term analyses for airplanes and so forth, where you can look into things like maintenance prediction. When are my elements, when are my components of the system failing? When do I need to do predictive maintenance and basically start replacing in advance to a problem happening, of course.
Sure.
So this is all very much data-driven. You have huge amount of data created. They need to be processed, transmitted, and stored somewhere, and that's the intelligence somewhere there in the middle. So if you look into here on 101 in the Bay Area and on 280, you have all these races of the different autonomous cars collecting data. The amount of data they are creating while they're just driving there is just huge. It's just immense.
Sure.
So they need to be processed, transmitted, stored, and then made sense of in all this. So the digital twin definition, if you will, in aerospace, it's really a representation of a current state of a manufactured product at any given point in time. And then they have also this parallel piece, a digital thread, which is a record of all states of a manufactured product or system over time from conception to disposal. So for us in the verification domain and in the system development domain, I took the liberty to kind of refine it a little bit for essentially a digital twin being a system under development, and the digital twin is a functional, correct, predictable, reproducible representation of the product or system at the appropriate level of fidelity to perform verification, performance analysis, and system validation tasks. So I basically took this definition as I've seen it in aerospace quite a bit and then refined it down to what we do in the verification world. And that's in the space what we define as digital twin in our environment. It actually connects to the bigger world in aerospace and automotive as well.
So Frank, circling back to this data-driven world you mentioned earlier, how does data fit into the digital twin picture exactly?
Well, it's data is like the fuel, all right, of all of it. So if you do your system design again and starting essentially from the high-level system spec, this device needs to fly, needs to have certain connections, needs to have certain speed and maneuverability. So all those requirements are defined, and now you refine the system with more abstract descriptions, adding more and more detail, where then essentially at one point you arrive at the chip implementation, which then goes back into the system. So what you can do with the data now, this is just the data refinement as you're developing it. But the interesting thing is you end up with different snapshots of your system as you're developing it, like a virtual platform, like an emulation model, which basically represents the chip within its environment, down to a prototyping board. And now you look at the data and you start applying the data you get from a real world system to those digital twins. You may actually, going back to the definition with aerospace, these digital twins are kind of byproducts of the development process here. You may decide that for certain aspects you need to build a custom digital twin, if you will, for specific purposes, and it's not necessarily a byproduct of the development flow when you want, for example, to model specific environmental aspects and so forth. But yeah, so the data is key to all it, because you're now taking the data which you apply, which you get in the real world, which you trace in the real world, and you want to apply that to your digital twin to see things like maintenance issues, to look at performance, to look at how much software load you actually get in an actual run. Was it actually planned
Right.
as you were architecting the system? And then it's going beyond the digital analog and the software piece. You can look into things like mechanical wear, reliability analysis, and can try to front load it with a digital twin as opposed to waiting until it happens and send in the service crew, right? So that's
Sure.
the idea for digital twinning here in that environment.
Okay, so Frank, what does this really look like for your average engineer?
Well, one of the items we have defined in our talks and our white papers is kind of how do you use emulation and prototyping in this environment, right?
Yeah.
So this is a system at the level of a board, if you will. So it's not really a full system of systems, although being in the world of emulation, I'm happy to provide more emulators and prototyping environments as needed. But you take your design for that system with its system environment, you compile it, load it into your emulator or prototyping system. You load the software on top of the processors into it. You may connect it to existing hardware. So you go connect it to an Ethernet bus, connect it to PCI Express. And now you're applying the actual data from that system as you have measured it. Or we have partnerships with test vendors, for example, as you have test environments. You apply the actual data to this digital twin setup, to this digital representation of the chip to be, which hasn't been manufactured yet, the chip and the system. So you run all the performance data and analysis analytics on top of that environment. So with that, you can look at things like performance, power, reliability, safety, and you can actually take into account the previous version of a chip, right? So you look into the previous generation, you look at the low power analysis of that chip, and then you look into your new RTL, your new system, and you're like, oh, if I tweak the software here and tweak this hardware there, I can actually get to a much better hardware software load, a much better power consumption, and so forth. So that's the principle of how it all hangs together.
Okay, so Frank, we touched upon this software side of things earlier, but let's get in a little deeper about that.
Okay, software is obviously, together with the data that fuels everything, software is the long pole in a lot of the developments because the complexity is just growing. A lot of those companies we got to know as chip companies, they're still chip companies, but the software developers are outnumbering them here. And if you look into the abstractions like a car here, you actually have different responsibilities throughout the flow again. So you have the microcontroller suppliers, the engine control unit suppliers providing you with lower level software. And then there's a big interesting back and forth going on between the system OEMs and the suppliers, like who writes the software, and there are abstraction layers in between, things like AutoSAR and so forth, where the system guy, if you will, the system team can do the software and has abstractions layers in between there. So software is a huge aspect in all this because it defines a lot of the interaction. And the hardware at one point is fixed. With software, you obviously do future revs in all this.
Sure. So I've heard about shifting left for several years now. Would that be applicable here?
Absolutely, absolutely. So it's really only a question on how far left you shift. So in a traditional flow, you would build the components, do the integration, and that's this classic V diagram as used in automotive. So you refine from your requirements going down, and then you build and you integrate. Well, the challenge with that, with everything taking so long, with a chip development taking you 12 months, 18 months, depending on the complexity, of course, it's quite an issue. So you want to do virtual integration early on. And that's where this whole notion of shift left comes in, where I essentially get my shift left of the hardware software integration by applying virtualization. So instead of waiting until my silicon is back from the fab, I start with my software development much earlier in the time, and that's where the shift left comes from, because I'm starting the integration much earlier.
So, Frank, what does shifting left really buy us here?
Well, in this particular case, it buys you higher quality, and it's what people really enjoy is the ability to have the software up and running very fast after the chip is back. So as opposed to hoping and praying while the chip is in production that the software might work, you essentially have already validated as part of your pre-tape out activities how your software executes on it. We have customers for which the booting of an Android has become a necessity for tape out, so they make that part of their checklist. So that's what it brings you, that after the chip comes back, the software coming up within hours sometimes, as opposed to weeks and months of praying and trying to bring it up in the lab. And that gives you this notion of different digital twins on the path of that, because you build, for example, a virtual platform early on, then you build a hybrid of this virtual platform with simulation, you connect it to emulation, to prototyping. So it's all different snapshots, if you will, of different digital development twins, digital verification twins on the path to development. And then at the end, you can go back and add more around it. Now I'm adding more of my system environment to it and build my digital twins for specific questions I need to ask around it.
Sure.
So what you do with the virtual platform, for example, you build this hybrid of a virtual platform with the more accurate representation of parts of your designs in emulation or in prototyping. So that allows you to serve many more software developers earlier. Hundreds of users can use a pure virtual platform. Then you add in things like the graphics component into it, and you want that more accuracy in a system like a prototyping system on emulator. And that gets you to your software development starting 6 to 9 months earlier. And by my definition of a digital twin as earlier, that's actually a digital twin pre-silicon, where you do all your verification before the silicon is available.
Sure. So since your badge says Cadence, I'm guessing Cadence has some solutions in this space?
Yeah, we definitely playing in this space. There are a couple of areas. Obviously, we play in the systems domain when it comes to the electromechanical, the thermal aspects. We have tools in that domain. The tools I'm representing in that domain are the emulation and prototyping environments, Palladium and Protium, Z1 and X1. Those are kind of, I call them the dynamic duo. They're often used together. They're very scalable. And a typical setup then might look like a mixed abstraction setup with hybrid usage. Might look like this diagram here, where I'm having some of the components of my system now in an emulator. So I'm putting some of the digital audio blocks, some of the mobile communications into the emulator. And then some of the connections, some of the navigation, I put into pure virtual nodes, and I connect all of it with RAID adapters. We call them speed bridges. So that's a typical hybrid, a digital twin, where you do software development, where you do analysis of performance, especially for the items which you have in the more accurate representation in the emulator. And a great example here is our partner NVIDIA. That's a public example here of their emulation lab, where they're doing software-based hardware tests. And it's really a digital twin. This one needs a lab, right? With all the execution, but it's essentially a digital representation of your design available before silicon is available, and you plug it in the PC and you see how the graphics looks like for the next generation device. So that's an example of a digital twin for verification as it is created pre-silicon.
Cool. Okay. So, Frank, way back in the beginning, you mentioned AI. Now, I would imagine that AI is posing a whole bunch more complicated verification problems.
Yeah, absolutely. So AI, there's a question now, how much power do you give your digital twin? If I'm now in the situation that I have in a car and I get all my data and I apply it back to the digital twin, even if it's for a subsystem only, I can do the analysis and look at things like maintenance, prediction to come, but I can also give it more power. I can make decision based on the data in the digital twin, the results of the digital twin, and can apply them to the real world. So that becomes much more challenging now. Now it becomes, if there's AI involved, if I have a digital version of myself standing next to me, so to speak. So this Frank Dash, is this neural network properly verified? Does he have potential outliers, or will he be as balanced as me all the time? Do I have all the training done? Is it secure? Can that Frank Dash be hacked?
Right.
Is he safe? Then there's a question around data, around all this, like who owns actually the data I put into all this? There are very interesting challenges to come, and it extends in that domain to things like social media companies and my data. There's this big discussion going on about who owns my data. The same will be true for digital twins, which we not only use for analysis, but now really use for making decisions in real life. So that becomes very interesting how the AI fits into all this, because you look at all the data and you make sense of it with AI. We at Cadence look at artificial intelligence and machine learning in three ways. There's the machine learning inside. So we have inside our tools, we use machine learning to improve performance, power area, and the implementation flows. We use it to choose the right engines for formal, to improve our testing and diagnostics. So that's really making our tools better. So the customer, besides the fact that it's attractive that I can say, hey, we use machine learning under the hood, which everybody kind of finds intrinsically cool and intuitively cool. If I could have implemented using a standard algorithm with the same results, great. But what the artificial intelligence really does here in the inside our tools, it kind of captures the knowledge and the experience of the designer a bit, which leads to the ML outside, where I'm automating my design flows. Now I'm really capturing what the designer does with the tools, and the tools are learning how the different blocks are flowing together and getting better productivity. And then last thing for AI and machine learning is the enablement piece, where we enabling our customers to do their designs. So in that there we have things like the hardware software co-design. So obviously my toys, Palladium and Protium, because of their capacity and speed and the way they work together, they're used by a lot of AI ML companies to verify the hardware software on those designs. And then of course we have in our Brethren business unit the IP team here. We have the Tensilica IP for machine learning. We have the right level of memory IPs and so forth, the design IP for machine learning and AI. So it's big for us at Cadence in those three areas, making our tools better, which is the inside bit, making a better use of our tools, the ML outside bit, and then enabling our customers to build their AI designs, right? It's a big item for us, and it's part of our big strategy, if you will, which we refer to as intelligent system design, which is based on the design excellence in our digital analog RF verification flows together with our IP, and extends into the whole software world. We talked about that. Extends into system analysis, and then into this area of pervasive intelligence, where you have machine learning inside, outside, and enabled by our tools.
All right, Frank. Well, I think that's all I have time for today. Thank you so much for joining me.
Thanks for having me, Amelia.
And before we go, you didn't forget to click that link, did you? There you can find even more information about Palladium and Protium platforms for system development from Cadence Design Systems. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, check out the Chalk Talk section of EE Journal. You can't miss it, it's right across the top. Or head on over to YouTube, youtube.com/EE Journal.